GenAI and MLOps Part 26. This episode has 5 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. Explain CI or CD for ML. Here's a strong way to approach it. CI or CD for ML. Machine learning CI or CD is the practice of automating the building, testing, training, validation, deployment, and monitoring of machine learning models using DevOps and MLOps principles. Unlike traditional software CI or CD, ML CI or CD also includes data validation, model training, feature pipelines, and model performance checks. The goal is to deliver reliable ML models to production faster, with consistency and automation. CI, continuous integration in ML. Continuous integration focuses on automating code integration, unit testing, data validation, feature validation, model training, triggers, experiment tracking whenever new code, data, or configurations are pushed. Automated pipelines validate and test the ML workflow. CD, continuous deployment or delivery in ML. Continuous deployment automates model packaging, containerization, model validation, deployment to staging or production. Canary or blue-green deployments, monitoring and rollback. Typical ML CI or CD pipeline. 1. Data ingestion and validation. 2. Feature engineering. 3. Model training. 4. Hyperparameter tuning. 5. Automated testing and evaluation. 6. Model registry and versioning. 7. Containerization using Docker. 8. Deployment to Kubernetes or cloud platforms. 9. Monitoring and retraining important components. Source control for code and pipelines. Dataset and model versioning. Automated testing infrastructure as code monitoring and observability. Automated retraining workflows. Popular tools: Jenkins, GitLab CI or CD, GitHub Actions, MLflow, Kubeflow, Docker, Kubernetes, TensorFlow. Extended from an MLOps perspective, CI or CD for ML helps achieve faster releases, reproducibility, scalability, governance, and reliable model lifecycle management in production environments. Nice. Let's continue. Question 2. What is CT in MLOps? Here's a strong way to approach it. CT in MLOps stands for continuous training. It is the process of automatically retraining machine learning models whenever new data, drift, or performance degradation is detected. Continuous training extends traditional CI or CD pipelines by adding automated model retraining capabilities to keep ML models updated and accurate in production environments. The main goal of CT is to ensure that models adapt to changing data patterns, user behavior, and business conditions over time. How continuous training works. 1. New data is collected from production systems. 2. Data validation and pre-processing are triggered. 3. Model retraining pipeline starts automatically. 4. Newly trained model is evaluated against validation metrics. 5. If performance is acceptable, the model is registered and deployed. 6. Monitoring continues for future retraining cycles. Common triggers for CT: scheduled retraining, daily or weekly or monthly. Data drift detection, concept drift detection, performance degradation. New business requirements. Benefits of continuous training: keeps models up to date, improves prediction accuracy, reduces manual retraining effort, supports dynamic real-time systems, enables adaptive AI systems. Challenges: retraining cost and infrastructure usage, data quality management, model validation complexity, risk of unstable deployments, monitoring and governance requirements. Common tools used: Kubeflow, MLflow, Airflow, TensorFlow. Extended Jenkins. From an MLOps perspective, CT is a critical capability for maintaining production ML systems that require continuous adaptation, monitoring, and automated lifecycle management. Great. Moving on. Question 3. What is reproducible training? Here's a strong way to approach it. Reproducible training means the ability to train a machine learning model multiple times and consistently obtain the same or very similar results using the same data, code, configurations, and environment. It is an important concept in MLOps because it ensures reliability, debugging capability, auditability, and collaboration across teams. For training to be reproducible, all parts of the ML workflow must remain consistent, including dataset versions, feature engineering, logic, hyperparameters, random seeds, model architecture, library and dependency versions, infrastructure and hardware configurations. Key practices for reproducible training include: 1. Version control: track code, datasets, models, and configurations. 2. Environment consistency: use containers and dependency management tools. 3. Experiment tracking: store metrics, Parameters, artifacts, and logs. 4. Fixed random seeds reduce randomness during training. 5. Pipeline automation use automated and standardized workflows. 6. Data lineage tracking track source and transformation history of datasets. Benefits of reproducible training. Easier debugging and troubleshooting, reliable model validation, regulatory and compliance support, better collaboration among teams, simplified rollback and auditing. Popular tools supporting reproducibility include MLflow, DVC, Docker, Kubeflow. Weights and biases from an MLOps perspective. Reproducible training is essential for building trustworthy, maintainable, and production-grade ML systems. Alright, next question. Question 4. Explain model packaging. Here's a strong way to approach it. Model packaging is the process of bundling a trained machine learning model along with all required dependencies, configurations, runtime libraries, and serving code into a deployable unit for production environments. The main goal is to ensure the model runs consistently across different environments such as development, testing, cloud, or production systems. A model package typically includes trained model files, inference code, pre-processing and post-processing logic, dependency libraries, configuration files, runtime environment details. Common packaging approaches. 1. Container-based packaging, using containers to package the model and runtime environment. Most common production approach. 2. Serialized model packaging, saving models in formats like ONNX, Pickle, Saved Model, or Torch Script. 3. API-based packaging, packaging models as REST or gRPC services for inference. Benefits of model packaging: environment consistency, easier deployment and scaling, faster rollback and versioning, improved portability, simplified CI or CD integration. Common technologies used: Docker, Kubernetes, TensorFlow, serving, Torch, Serve, MLflow, ONNX. Runtime example: workflow. 1. Train the model. 2. Serialize the model. 3. Add inference scripts and dependencies. 4. Create a Docker image. 5. Deploy to Kubernetes or cloud platforms. From an MLOps perspective, model packaging is critical for reliable deployment, portability, scalability, and maintaining consistent inference behavior across environments. Let's keep going. Question 5. What is inference optimization? Here's a strong way to approach it. Inference optimization is the process of improving the speed, efficiency, scalability, and resource utilization of machine learning model predictions in production environments. The main objective is to reduce inference latency, improve throughput, and lower infrastructure cost while maintaining acceptable model accuracy. Inference optimization is especially important for real-time AI applications such as chatbots and LLMs, recommendation systems, fraud detection, computer vision, voice assistants, edge AI devices. Common inference optimization techniques. 1. Model quantization converts model weights from higher precision, FP32, to lower precision, int8 or FP16, reduces memory and improves speed. 2. Pruning removes unnecessary model parameters or neurons, makes the model smaller and faster. 3. Knowledge distillation trains a smaller student model using a larger teacher model. 4. Batching processes multiple inference requests together for better throughput. 5. Hardware acceleration uses GPUs, TPUs, or specialized AI accelerators. 6. Model compilation and optimization engines optimizes computation graphs for specific hardware. Popular tools and frameworks: TensorRT, ONNX, Runtime, TensorFlow Lite, OpenVINO, Torch. Serve key metrics in inference optimization: latency, throughput, memory usage, CPU or GPU utilization, cost efficiency. From an MLOps perspective, inference optimization is essential for building scalable, cost-effective, and high-performance AI systems capable of serving production workloads efficiently. On to the next one. That wraps up this episode. Nice work practicing, and see you in the next one.